So this is a really involved practical, investigating stationary waves on a string. But basically we're investigating one equation, which is given to us as f equals 1 over 2L multiplied by the square root of t over mu. F is the frequency of the stationary wave. L is the length of the vibrating part of the string, T is the tension in the string, and mu is the mass per unit length of the string. Now, what on earth are we going to reference here? What could we be trying to discover that we can check? Well, this is quite difficult. So what I would say is let's reference the equation itself. So whether we can find a derivation of the equation or at least some explanation of how the equation works online, and then we can reference that. Let's start with that because that's going to probably be the best place to start. There's a nice reference for what they call standing waves, which is just another word for stationary waves. And you can see the equation appears where the speed of the wave is the tension, the square root of the tension divided by the square root of m, but m is defined as the mass per unit length. M is the mass per unit length of the string, so that's in agreement with what we've said, it's just we're using different symbols. V equals f lambda, that equation just falls out. So that's absolutely fine. We could reference that. It also has this nice diagram at the top where it shows what the experimental setup is going to be similar to. So this is a nice one to reference. So there we have it. There's our reference for the derivation of this, which I'm not going to go into detail about, but that's the equation. So you can see there are 4 variables on that equation. And if this relationship is true, then we can say that it is as expected. And if this relationship is not true, then it's not as expected. But there are 4 variables. So we have to straight away start deciding what our 3 practicals will be. In one practical, we'll have 2 variables and the other 2 will be constant. In the next practical, another 2 variables, the other 2 will be constant. And in the final practical, 2 other variables and the other 2 are constant. I suppose we could do more than that, but that's what we're going to do. So in each case, let's have f, that is the frequency of the stationary wave, f, and I'll label that as frequency of wave, will be the dependent variable, dependent variable, and we'll worry about how to measure that later. So the 3 practicals, we're going to have practical 1. On practical 1, let's have L as the independent variable. L, that's the length of vibrating string, not the whole string, just the vibrating string. Let's have L as the independent variable and have T and mu as the control variables. And we can talk about how we're going to control them, keep them the same later on. Practical 2. Well, in this case, let us have T as independent variable and the other 2 as the control variables. And finally, with practical 3, what we're going to do is have mu, the mass per unit length, as the independent variable, and we're going to control L and T. Now, I could record in this, but I'm not going to for space-saving reasons, but I could record in this is how I'm going to keep these variables controlled. And that depends on our experimental setup. Well, I'm going to borrow from this reference for the experimental setup. And the way we're going to do it is we're going to have a vibration generator connected to a string which is going to vibrate between a vibration generator and some sort of pulley or jockey wheel. Just like that. Now the string is going to pass over the jockey wheel and have masses suspended from it, just like that. We are going to tie the string onto a clamp stand, which is going to be G-clamped down, and we're going to do that so that there's not too much transverse tension on this vibration generator, which could damage it. We're going to place a bridge that can move left or right, and that allows us to vary what L is, where L there is the length of the vibrating part of the string. The mass here is going to be providing our T, tension. It will be equal to the mass that's suspended over the edge multiplied by G, the gravitational field strength. We'll have the signal generator connected to the vibration generator, and that's going to also be connected to a frequency meter. So we'll be able to measure the frequency. That's going to measure F. So we've got our T, F, and L. We still need our mu. Well, we're going to measure the entire length of string, the mass of the entire length of string, and the entire length of string to determine what mu is for each string that we use. So how am I going to keep T controlled for practical 1 and practical 3? I don't change the masses. How am I going to keep mu controlled for practical 1 and practical 2? I don't change the string. How am I going to keep L controlled for practical 3 and practical 2? I'm not going to move the bridge. And so obviously when L is our independent variable, we do move the bridge. When T is our independent variable, we do change the mass. When mu is our independent variable, we do change the string. So there we go. That's the starting point. Now we can start thinking about gathering data. Well, I'm going to have lots of different bits of string by the end of it. So let us add to this that for practical 1, we're going to use string 1, whatever that is. And we'll label it string 1 later. For practical 2, we're also going to use string 1. So when we do practical 3, we won't have to repeat some of the measurements because we've done the ones with string 1 already. So we can use different strings, just like that. Use different strings. I'm just making a note of that because we're going to have to tally together our results at the end, so it's better to have some idea. But whatever one I use for the first one, I'm going to call that string 1. Now for practical 1, we're going to have a tension equal to a certain amount, which I'll work out in a second, which will be fixed, and we're going to have a mu equal to and some amount, and we'll figure that out in a second. But that will be string 1. And then we're going to need a table of L versus F. L in, let's say, meters, and F in hertz. And we'll leave some columns to the right in case we need them later. How many data points? 1, 2, 3, 4, 5, 6, 7. Let's just get 7 data points. And hopefully that will be enough to show what we want to show, which is the relationship between F and L. Now already I can anticipate what that relationship's going to be. F is proportional to 1 over L. So there's a few ways of doing this. I can take the log of both and then try and get a straight line and find the gradient to be equal to -1. Or, alternatively, I could calculate the reciprocal of one of these. So if I'm going to plot F on the y-axis, let's do 1 over L. So we've got that on the y-axis versus 1 over L, and the gradient should be half square root of t over the square root of mu. So we are going to have a L in meters to the -1 column right there, which we will plot our graph from. That will become the x-axis, and that will be the y-axis. And let's just finish off our table. Now, I'm not filling in any of the numbers until I've set up the experiment. So let's get it all set up, ready for the first practical. Now, I found this signal generator actually a bit better than the newer ones. The newer ones have a fuse inside them that when you connect them to a low impedance device tends to fry, so I prefer to use this one. It's older and therefore better. There's our frequency meter, there's our vibration generator bobbing up and down quite happily, which will be tied, we'll have a piece of string tied to here, which is G clamped there. We'll place a bridge over here somewhere. There's the pulley. I've tried to make it so that the pulley and the vibration generator is all in line. See that there? That's what we're going to use for the bridge. It's a fairly sharp point on the top of that. Fine. And then we've got a whole bunch of different strings and a balance and a ruler so we can measure the mass per unit length. So let's pick string 1. So it turns out I've only got 4 different gauges of fishing line. This says 8, whatever the hell that unit is. That's 2.5, whatever the hell that unit is. That says 0.8, whatever the hell that unit is. This one, don't know, no clue. 𝗟𝗶H, no idea. So let's start from this one because it's already open. And what we're going to do is we're going to take our ruler and we're going to measure a metre, maybe 2 meters of this, because it's not going to have a lot of mass. So we're going to want to measure a couple of meters of this. Oh, there's an horrible knot in it. Let me just get a pair of scissors and we'll cut that horrible knot off. Oh, that bit's loose there. We'll measure a couple of meters of it so that we can measure the mass per unit length. And that's the property of the string that we are interested in practical 3. So for now I just have to make sure I'm using the same string so that it is controlled. That's 1 meter. That's 2 meters. If I'll be able to measure 2 meters worth, well, let's find out. Let's just cut it off. And let's see if I can measure 2 meters worth. Well, I dropped the string on the floor, and I'm not going to tell you how long I've just spent looking for it. This is the downside to using fishing line. It is very difficult to see. So to measure the mass per unit length, I'm going to coil it up, not knot it up, but coil it up and just plop it in. No, that's not going to work. Let me tape it and measure the mass of tape separately. Our friend masking tape. So let's get that off there. Let's 0 that. Right. Now, where's the end of this damn fishing line? Oh no, don't tie a knot in it. That's the worst thing that can happen. Oh, this practical's such a pain in the bum. Okay, so 3 fingers, loosely wind it. There's 2 meters, as close as I can measure. Tape it so it doesn't just spring off. 0.39 grams for 2 meters. There we go. So that's going to be 0.39 plus or minus 0.01 grams divided by 2.00. Let's do it to the nearest 4 millimeters. So there's a millimeter on each side of the ruler, twice because I used 2 meters, 0.004 meters. That will give me the mass per unit length in grams per meter, and I can calculate the uncertainty from that as well. So let's get my calculator out. 0.39 divided by 2, used a calculator for that, let's say 195, and I can change it later. Plus or minus, right, so percentage uncertainty of this one is 0.01 divided by 0.39, well that's the relative uncertainty. Relative uncertainty of this one, 0.004 divided by 2. Add them together, so that's the relative uncertainty in this, so multiply it by 0.195, and that gives us the, that's my frequency meter beeping, that gives me 0.0054, so I should have put an extra 0 in here. 0.0054 unit is, grams per meter. Ran out of room there. But there we go. That is the measurement of the mass per unit length of that string. Let's get it all attached. Right, so we don't have to use the full 2. We don't have to use the full 2 meters, which is good. I'm going to use a bowline here, which is quite fiddly to tie. loop it around the vibration generator, and then pass it through the pulley the other side and tie another bowline the other side. Now my reason for tying a bowline is because they don't slip. I'm going to put this string under tension, so I should have goggles on or eye protection while I'm doing this in case it snaps. And if you don't know how to tie a bowline, my advice to you is learn how to tie a bowline. It's the most important knot. Right, I've put 300 grams suspended from the end there. I'm just going to loop it around this vibration generator once, like that, and insert the bridge. Not going to be able to get a meter with where this is, but I can move this stand that it's tied to. I can move that further back. I can still move all of this. So I will. I'll move this further back so we've got a bit more room. There we have it. We're all set up, and it should be quicker to set it up next time. You can see that we've got a bowline here tying this string, which is looped around this vibration generator. Let's just turn that right down so you can see that it is just looped around it. It's not tied on, it's not passing through the hole, just looped around it. Turn that back up again. The string can be very difficult to see, so I've got a piece of card here, so I've got some contrast. Then I've got the bridge, which I can move around. And then the mass is suspended over the edge, which won't be swinging. And that is the experiment set up with our frequency meter. Now, a word about this frequency meter. It does not work very well on sine wave. We have to switch it to square wave, and it will give us frequency. Now, it's fine on sine waves where the frequency is above about 50 hertz, but for low frequencies, we will switch it to square wave to get the frequency measured, switch it back to sine wave again afterwards. Right, let's go see if we can find a harmonic, perhaps our first harmonic. So I'm going to very carefully measure. My independent variable is the length between where it was vibrating and the bridge. So let's push the bridge in place and very carefully measure 1 meter. Uncertainty in this measurement is going to be perhaps even ½ centimetre if I'm being generous with my uncertainties. Because of the size of the pin on the vibration generator that's vibrating up and down. But I would say that's a meter of vibrating string right there. Let's change the frequency until I get the first harmonic. And switch it up, down, that's amplitude. Hang on. Oh, so around about there somewhere the amplitude grows quite considerably. You might just about be able to make that out in the screen. There, small amplitude, reduced frequency, and the amplitude grows. Reduced frequency further, the amplitude reduces again. So there's resonance around there somewhere. Now I used the equation to help me here and calculated that I should be getting resonance at about 61 hertz, and I'm at about 61 hertz nowish. If I increase the frequency, the amplitude reduces, back down to 61, reduce it further, amplitude reduces. But it's really difficult to see. What would be better if I look for the second harmonic. This is the first harmonic, and we're looking for the biggest amplitude in the middle. That can be quite tricky to get. Instead, I could look for the second harmonic. So let's do just that. Second harmonic should be around about 120 hertz, and we'll see a node right about here-ish. Oh, I should also point out that the string is vibrating this way, so although it may not look like a lot of amplitude here, when you get down level with it, down about here-ish, you can see it. Obviously, I've got my safety glasses on. You can see the amplitude far more there. Maybe I'll get this like this, so you can see I'm not just telling you porcupines. Possibly be able to ignore that. So that way around. Yeah, so you can see there the much larger amplitude. That's what I'm looking for. You can't see it very well from on top there because the string is vibrating vertically. So I'll have to position the camera a bit more intelligently. Why it takes so long to do all these things. Right, so I reckon it's going to be at about 120 hertz. So let's... Oops. About there-ish, and now I'll try and find that node. There. That frequency there. So you can see we've got big amplitude over here, small amplitude going to big again. The camera can't pick it all up. There's too high a frequency. There's resonance. There's too low a frequency. So after that frequency, around about there. And that's what I'm going to write down. And I'll stick with doing my... No, I'll do the first harmonic. I won't do the second harmonic. It's not really any easier for you to see. So I'll do the first harmonic. We'll go with the 61 hertz. Yeah, changed my mind. So length was 1.000 meters. Frequency was 61. Now this measures to... Just drop that bit down again. Yeah, this measures to 2 decimal places. So I have to write it as 61 point. Let's go find the resonance. Wow, I mean, first harmonic, that's a huge amplitude right there. See that against the white card, the red card. So be careful because the bridge keeps moving. So I made a measurement, wasn't happy with it, made another one, then the bridge moved, so it's currently 64.21. So that's what I need to write here. See, I've changed it, I'm going to change it again, 64.21. Oh, you see, the whole desk is vibrating, which is vibrating the camera at that particular frequency. It's making all the stand resonate and everything. No wonder the bridge moved off. So, right, what we're going to do now is change the length. So we're going to reduce the length. Let's reduce it to 0.800. But before we do that, let's write some things down about... let's turn this off. It's vibrating all over the place. The internal circuits warm up, so you shouldn't really switch the signal generator off because it does affect its ability to keep a constant frequency, but it doesn't matter. We're using a frequency meter, so it doesn't really matter. So we do want to write down something about uncertainties. And I reckon my length, the uncertainty in my length, is going to be maybe 5 millimeters, as high as that. And I think the uncertainty in my frequency is 0.01 hertz. It's a pretty good meter. So I'm going to leave it like that. Now let's carry on with the measurements. 80, so that means I've got to move the bridge. Oh, this practical takes an absolute age to do. 80. 80 would be there. I could use blue tack to stick it down. I'll leave it like it is. Put the card in the middle. Let's go find that first harmonic. Okay, so I think I might have found it. Let's just the card there. Big amplitude, as you can see. If I can prop the card up somehow so we can... Oh, there we are, look. Big amplitude. If I drop the frequency down a bit, the amplitude drops. Put it back where it was. Increase the frequency a bit. Drops a lot. That frequency there seems to be the frequency that gives us the maximum amplitude. Thus, that is the first harmonic for 80 centimeters, 79.48. And then we move on like that. So now we do 0.6. Don't know how many of these we'll do. Probably won't do 7 of them. And we repeat like that. Right, so distance has been carefully measured to be 60, not like I'm doing here. 60. Let's get down nice and low. This is in the middle. Let's increase the frequency. Around about there somewhere. Reduce it. Oh, nice. Reduce it a bit more. Drops down. Increase it. Increase it. Reduce it. Reduce it. So it's around about there. That's 104.8. Oh no, look. The resolution's changed. 104.8. I better make a note that the resolution's changed as well. There we are. Just made a quick note that that changed. 104.8. Bush. Let's do some more. Should we do 50 centimeters? Well, I'll tell you what, I'll do the rest and I won't show you each one because it's now just a bit of routine. This is future Keith here. So I did the rest of the data and then my camera overheated and started recording audio only. And I didn't notice this until I put all the videos together and started editing it. So I'm recording this the next day. This is the data that we have captured. You can see I've only got 5 data points in the end. I didn't want to go above that. So I recorded the tension as well. We used 300 grams suspended over the edge of the bench. So that is 300 grams with 2% uncertainty on the masses. I reckon it's about right. Gives us 0.006 kilograms of absolute uncertainty. There's no uncertainty I'm going to add to the gravitational field strength. So that gives us an absolute uncertainty on our tension in practical 1 of 0.059. So to get the tension, I just times 0.3 by 9.81. To get the absolute uncertainty, I just do the 3% from this plus 0%, so that's 3% of that is that. That's 3% of that. So that's fine. So I've got enough data now on practical 1 to do the analysis in a little bit, and that took me about 45 minutes to do. I also did practical 2, and the camera still was broken when I started talking about what I was doing with practical 2. So let's see if I can hide the data, because while this bit of the video appears, you won't yet have the data. There we go. Right, okay, so we need to think with practical 2, what was our independent variable? If we look back, it was actually the tension was our independent variable for practical 2. Tension, keeping everything else, oh, don't look at the data yet, keeping everything else controlled. Come on, future Keith. There we go. Well, that means that everything else has to be kept the same. So let's go with 1 meter of string vibrating. I've chosen to keep 1 meter because it's a fairly big length and it means that it's easier to see the first harmonic if the string is vibrating. It's a nice long string. Short strings, it can be harder to see the first harmonic. That means I've got the same uncertainty as I had before when I was measuring L, the vibrating length of string, which before, let's just move this down, I had decided that because of where the string was attached to the vibration generator, I wasn't quite sure. I reckon about 5 millimeters of uncertainty. I'm going to stick with that 5 millimeters uncertainty with the length and say that that is the uncertainty in my fixed length. My control variable is that length. Anything else I need to say? Yes, so I'm still using string 1. So mu is the same as I had before, which remember I measured as 0.39 grams, plus or minus 0.01 grams. I divided that by the 2 meters of that string, and I reckon because I used 2 rulers with 1 millimeter uncertainty at both ends of the ruler, then that adds all the way up to 0.004 meters of uncertainty. So that gives me this number divided by that number gives me that number, and you get the uncertainty by working out the percentage uncertainty in mu, adding that to the percentage uncertainty in the length. That gives you the percentage uncertainty in this. So multiply that by that percentage uncertainty to get the absolute uncertainty. But it's exactly the same as we had last time. I'm keeping that as a control. Anything else I need to say? Yeah, just be careful because this is in grams per meter, not kilograms per meter. So we will have to times this by 10 to the power of -3 when we do any calculations later on. Right, so we are changing our tension. Well, I can't change the tension directly. In the experiment, what I was actually doing is suspending some masses over the edge, so I can change that mass. That mass becomes the independent variable. That is m on the left there. And the masses have an uncertainty of about 2%, I reckon. I looked it up once upon a time, and I think it's about 2%. You could look it up and reference it, of course. Then what have I got? Frequency meter is measuring to the nearest 0.01 hertz. And then, because I want to plot frequency versus tension, this is the relationship that we looked at, that I referenced at the beginning. This is a relationship rearranged into the form y equals mx plus c, where the independent variable is the square root of the tension. And you can see it looks like this. Because of doing that, I need to get the square root of that. So that means I need to multiply the mass by g and put it all under the square root, give me these odd units of newtons to the half, square root of newtons, and that's what's going to be plotted on the x-axis. But I can calculate that afterwards. Don't need to do it yet. So m is the independent variable, f is the dependent variable. That's what I expect the relationship to be. So I'm going to go and gather the data. I'm ready to go and gather the data for practical 2. And now I'm going to pass back to past Keith. So we're going to start with 100 grams, then add 200, 300, 400, and so on. Everything else will be the same. Everything else will be as we expect it to be, and I'll fill in the data here. Ah, yes, I need to have that 1 meter here measured, though. So let's measure that 1 meter as accurately as I can. There we go. I've got the uncertainty on it. That'll handle the inaccuracy. Right, now I can make my measurements. 100 grams. 100. What's the frequency where I get my first harmonic? Right, so I reckon that should be around 35 hertz. So I've got it on about 35 hertz to start us off. Let's have a look. Pretty big amplitude. Just position that somewhere in the middle. Let's increase the frequency slightly. Well, that's even bigger amplitude. That's even bigger. That's gone smaller. There, that looks like the right one. It might not be coming out very clearly. Try and get the light at the right angle. So it goes from there all the way up to there. Half of that's the amplitude. Might not be very clear on this, but there we go. Hopefully you can see that. So that's actually 39.07. 39.07 hertz. A little bit higher than I thought it would be, but that's okay. Now let's bang 200 grams on it. So we expect this to be about 50 hertz. Let's turn it up to about 50 hertz and see what we've got. Let's see where we are. Okay, so give it a little turn. Increases. Increases, increases, increases. Oh, it's going down. The maximum seems to be about there-ish. So hopefully you can see the reflection coming off the string, which makes it so you can see it goes from there all the way down to there. So I've got a pen. From there all the way down to there. That's the maximum amplitude. Yet again, slightly higher, 53.66. 53.66. And then we do the calculation again for the next one. Let's do 300 grams. Gives us a starting point. 300 grams, we expect it to be about 61 hertz. Increase it to about 61. Have a look. There's almost no amplitude there at all. increase. Now we're going to hunt around here for it. Oh, I haven't changed the mass yet, you plonker. I was thinking, why is it so much higher than I expected? I haven't changed the mass, look. What a plonker. 300. Now, do I have to do 300? No, I've already got a 300. Look. These were 300 grams. These were 300 grams. I've already got it. 1 meter, 64.21. I don't need to do that one again. So let's do 400 grams. $400 grams. Now let's check what we think 400 grams should be. Luckily I've got my calculator here, 71 hertz. Let's go back over here. It's supposed to be around 71 hertz. Let's have a look. Big amplitude, bit higher, bit higher, bit higher. Oh, it went down. It's about there-ish is the maximum amplitude. 72.14. Look how quickly you can do this. Let's do 500 grams. So 500 grams, let's type it into my calculator. I expect about 79 hertz. $500 grams. Card is still right in the middle. I expect 79 hertz. Let's just put that up to about 79. Pop it here. Near enough, 79. Oh, that's better. Tiny bit higher. It's around about there. Oh, it's a bit higher, 79.94. 79.94. And so on. So I'll take the rest of the data, you don't have to watch it. And there we have it. I can turn that off. All the data recorded. Now that's going to be easy enough to calculate. So I could just get my calculator. I could use a spreadsheet, but I'm just going to use my calculator. Like that. 9.81 square root. Pop that into the calculator. You can see there's annoying glare from the light up there. Doesn't matter. Maybe I'll tilt the screen slightly. Right, so that's the square root of g, and then it's 0.1 square root times, actually. Let's just put that up on the stack. 0.1 square root times. So this is going to be 0.990. Let's go through significant figures. 0.2 square root times 1.40. Should we go decimal places? Let's leave it 3 significant figures, because that's 3 significant figures. Now, I'll tell you what, let's do 4 significant figures. And I'm going to do 4 because I want to keep a guard digit. So let's do a 5 on the end of that. And for 0.2 square root times, let's do a 1 on the end of that. 0.3 square root times 1.716, and then we can go 0.4 square root times 1.981, 0.5 square root times 2.215, 0.6 square root times 2.426, and then finally 0.7 square root times 2.620. It doesn't take very long to do those calculations at all. Good. And while I'm here, I might as well fill these in as well. That's just a bunch of reciprocals. I've used 4 significant figures for these because they are 3 significant figures and I want to keep a guard digit. That's 4 significant figures, so I've given that one to 5. Now, before I move on to the next practical, one of the things I want to do is just write down the equation for each of these here in the correct form. So the equation we're using is this. In the first one, we've got L as our independent variable. So we'll have f is equal to the square root of t over 2 lots of the square root of mu, I'll write it like that, multiplied by 1 over L, where we are going to plot this on the y-axis, this on the x-axis, and this will be the gradient. And they should have a y-intercept of 0. Just like that. We can do the same thing for this one here, where it's root t. So we're going to put f is equal to, and now this is going to be 1 over 2l root mu multiplied by square root of t. And we're going to plot this on the y-axis, this on the x-axis, this should be the gradient, and once again the y-intercept should be 0. We'll have to check and see. So I know exactly what I'm plotting. This is t. I could put this as the square root of t in newtons to the power of minus 2. If I wanted to, I might put that in brackets just to show it's the same thing. And there, L to the minus 1. So you can clearly see what we're plotting where. And I can even take it a step further. And I could write down something like y-axis, x-axis. And I could do the same for this one, although I've scribbled on that one. But I can write down here y-axis and then x-axis, something like that, just so that I know. It's all about making it clear to myself what it is I'm doing. Now, practical 3. We've got data for this particular string. If we choose, let's go with 300 grams suspended from the edge and 1 meter, then I can yet again use this particular data point in the next table. So for this table, we're going to have mu, which means we've got to calculate mu for each string. Well, I've already got string 1. I already know what that is. Use string 1, use string 1. So I already called it string 1. I knew the mass in grams and the length. I don't want to use the same L because that's going to get confusing, or the same M because that's going to get confusing. So let's use subscript S in meters. That was fine. I used 2.000 meters. That's how I measured it. And 0.39 grams. And that allows me to calculate mu in grams per meter. Grams per meter. And I've already done that calculation for that one, so I can just write that in. 0.0195. Oh no, that's wrong. 0.1950, because we've got our uncertainty as well. And so I might even just have a separate column here for uncertainty and have that as 0.0034. 34? 54, I can't read numbers. And I know how to calculate that uncertainty, so that's fine. So I need some more bits of string. Well, I've got 3 more. So let's measure string 2, and then leave space for string 3, string 4, and extra space in case I mess up, because I already did with string 1, where I wrote the wrong number. But then what I need to do is, I want to make the measurements at the same time. I don't want to have a bunch of bits of string which I've had to label. As soon as I've measured the mass per unit length of the string, I want to use it. Otherwise, I'm going to lose track of all these little bits of string. So, finishing off my table, don't just present a list, it should be a table. Mistakes are allowed. You're allowed to make mistakes as long as you correct them. Right, let's go with string 2 then. This one was string 1. So let's go with this one as string 2. Maybe that's the diameter, 0.45 millimeters. That's 0.26 millimeters. A little bit flimsier. So let's use that. Let's go with 2 meters of it. Now, because I've already shown once how to do this, I don't really want to demonstrate how to do it again. So I'm just going to do it. Lay the string on the ruler. Let's go with 2 meters of this. It's got a much smaller diameter, so I suspect it will have a much smaller mass per unit length. Assume that it's the same fluorocarbon strings. So that means that they're going to have the same density, and hence there'll be lower mass, which is something I need to... Oops, there we go. Something I need to think about, because if my mass is too small, I'm not going to be able to make a measurement on my balance. Now, I think it'll be okay. Just hook the string into the edge there. I think it'll be okay with this balance. So let's just take the balance. They work better on a hard surface. I think that's what they're calibrated on. So let's just drop the balance down there. Little thing to hold it. Where'd the bit of string go? There it is. There it is. Right, so there's my 2 meters of string. I'm going to coil it around my fingers like I did last time. Don't want to stretch it or anything. I'm going to use a little bit of tape. Oh, let's zero it with a tape in. There we go. A little bit of tape just to hold it still. Let's just check that's 0. Yeah. Just to hold it so it doesn't unwind while I'm doing the measurement. Come on. There we go. 0.17 grams for 2 meters. So here we go. 0.17 grams, 2.000 meters. Mass per unit length. Out comes the calculator. Calculator? Calcia now. Oh, I say that joke so many times. There we go. We've got 0.085. I might need some more zeros after that in a second. Let's just check the uncertainties. So 0.01 divided by 0.17. Almost 6% uncertainty on that. Wowzer. That one there is going to be 0.001. I think I said 4 last time, didn't I? 0.004 millimeters of uncertainty in 2 meters. Nothing. Add them together, 6.1% uncertainty, which I can then multiply by that, so 0.085 to get the uncertainty in that. Yeah, we do want one extra significant. We want 4 decimal places so that they match. 0.0052. There we go. So I'll fill that in as and when I use these bits of string. Now, the experiment I'm doing is varying mu as my independent variable. So on my table here, I'm going to have mu in, let's have grams per meter, just like that. And they're all going to have different uncertainties, but I've got that recorded here, so I could use that when I draw the graph later. But actually, looking ahead, I know that I'm going to need the reciprocal of the square root of mu. And so that's going to affect the uncertainty. So I might have to leave a column for that uncertainty later, but it doesn't matter. We'll just get the data first, and we'll deal with uncertainties later. Then, of course, frequency in hertz is our dependent variable. Now, in this experiment, we are going to choose to use a mass of 300 grams suspended on the string and a length of 1 meter. So we're using this data point here as well. So I can actually fill in my first string already. 0.1950 plus or minus that, and the frequency was 64.21. So now let's go with the second string, that's string 2, which is 0.0850. I better draw some lines on my table. And let's find the frequency of the first harmonic. which means I've got to take the old string off. So let's take that bit off and load it first. Obviously, I'm still wearing my eye protection. Fail on competency 3 again. Let's just straighten that up. Keeps moving. So this is the old string here. I don't want to get it mixed up with the new string. So I'm going to coil it up carefully. And I'm going to tape it. And I'm going to label it in case I start wondering what it is. Label it string 1. Hopefully I won't need to use it again, actually. But just in case I do, I will know what it is. There it is. Label it. I'm just going to lay it on my desk and label it string 1. String 1. So let's just move the camera so you can see what I've done. String 1, and there it is. Chuck it in the bin if I don't need it. Right, let's get string 2 out. There we go. We'll use that tape later. There it is. No, not in that. No, there's not. Ha, 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 ha. Right, let's tie some bowlines. And that's the first bowline side, although it's out of focus so you can't see it. Hey, focus on my bowline. No, the camera's not going to focus on that thing. Right, anyway, let's loop that over there. Nice and tight. That's going to wrap around there. And then I want a bowline on the end. Lots of string to play with to tie my bowline on the end. But it is quite difficult to tie knots in this string because of how fine it is. So give yourself plenty of extra string so that you've got something to grab hold of. There we go. So there's my bowline tied on the other end. You see that there, hopefully. We're going to go with 300 grams because that gives us the correct tension. Oh, I've lost a bit of string. Where'd it go? Ah, I tied it on. That's why I tied it on. Like this. This bridge shouldn't have moved because I blue tacked it down, but let's just measure it. Loop that around there. Come on, loop it around the vibration generator. There we go. Oh, look at that, it's still 1 metre. Move just the teeniest of bits. 1 metre, look at that. So we've got that, string is set up correctly, put my board for contrast there, keep the workspace tidy. That's now ready. Let's put on the frequency meter. Let's do a quick calculation of what frequency I expect to get. That gives me an idea of where I'm looking for the frequency of the first harmonic. Now, my quick calculation station should be about 93 hertz. All right. Oh, we're nearly on 93 hertz already from the last time. Rattling, let's just tighten that up a bit. Okay, so let's get you down low so you can see the wave that we're trying to get. That's our about 93 hertz, gives us a starting point. It's a very fine string, very difficult to see. But as I increase, it's very fine, very difficult to see. Maybe it would be better if we look at it through an angle like that. It's not focusing. Big amplitude, small amplitude. Big amplitude, small amplitude. So increasing frequency, it goes through there. That must be the frequency of the first harmonic, 98.34. 98.34 hertz. A little bit higher than we wanted, but it still counts. Oof, I've got to go change the string again. There we are, string 1, string 2. Let's go pick string 3. String 3. It looks like it's going to be that one. Right. So we have our data for string 1 and string 2. Let's measure the mass per unit length for string 3. And given that these numbers seem to be reducing in mass per unit length, I'm probably going to have to do more than 2 meters. So let's measure 3 meters of string 3, just so that I can get a decent measurement of the mass. Can't find the end of the string. Where is the end of the string? No, it's already hooked there. So let's try and unhook that. There we go. Got it. Oh, it's very fine, this string. I can barely see it. Can you see it? It's a very fine string. So let's get 3 meters of this. That might not even be enough. I have to get a 4th meter. Let's hold it lined up with... Okay. Lined up with that end there. To that end there. Oh, I can barely see it. Oh, I dropped it. I dropped the real string. Right, so that's 3 meters. I will cut it. And if I have to measure another meter, so be it. Let's lay it there and hope that nothing blows it off while I make sure that the end of this doesn't keep unraveling. Okay, so old masking tape method. Zero it with the masking tape on. Let's just get... Oh, it's so fine. Where's the end of it? I can barely see it. Definitely going to be wearing goggles while I use this in case this snaps. Right. Let's coil it up loosely enough. 3 meters. Of this. Like that. Tape it so it doesn't unravel. Wow. That is a problem. Well, it must be measuring it because look, that says negative 23 and the masking tape by itself is only 15. Yeah, they must be measuring it. Let's try that again. All right, so there's that. Hold that in place. Okay, well, let's do it like that then. Let's do the difference. So, masking tape by itself, 0.15. Masking tape with string, 0.23. So that is 8. Let's try that again. 0.08 grams. 0.08. Wow. That is almost nothing. 0.08 grams. Now, it's worse than that when I consider the uncertainties, because I've had to make 2 measurements of mass. And so I have to add the uncertainties of those 2 measurements of mass together. Let's just try and do it like that so there's not a lot of glare on the screen. So it's 0.02 grams divided by the 0.08. 25% uncertainty. Yikes. And I don't really want to use multiple meters of this string. Don't really want to do that. But that's what I've got, so that's what I'm going to have to write down. Let's just do it. So it's string 3, 0.08 grams, a length of 3.000 meters, and of course that's going to have more uncertainty as well. Let's do the calculation. Let's turn rotation off on this. Let's do the calculation. 0.08 divided by 3.02. I mean, that's one significant figure, isn't it? Let's just record it at the same number of decimal places. 267. And now for the uncertainty in that. So we know it's 25% uncertainty in this, and I could write that down somewhere. And the reason how I got 25% uncertainty. But actually, I don't need to worry about that for A-level. Just doing it is enough. So, what was the uncertainty in my length measurement? when it was 2 meters. My uncertainty in my length measurement was, no, not there. Go back another one. Oh, I must have recorded it somewhere. Ah, there it is, 0.004. So it's a millimetre on either side. Well, I've used 3 metre rulers this time, so it's 0.006. So 0.006 divided by 3 still gives me my 0.2% uncertainty, which is pretty much nothing. When I add it to the 25% uncertainty, it still rounds to 25% uncertainty. And that 25% uncertainty multiplied by that, so multiplied by 0.26, blah, 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 0.0067, which is why I've recorded that to 4 decimal places so that it matches. Yeah, that's pretty significant. Huge error bars, but okay, that's what we've got, that's what we're going to use, so let's get that string. Where did I put the string? There it is. Let's get that string on the stand and do the same thing I did here. I'm not going to show you that bit because you've seen it before. That string was so fine, I was really worried about breaking it. But there it is, running along there, and with the mass suspended, not quite touching the floor. It actually seemed to stretch a bit because it was such a fine string. I don't know how good these results will be. Luckily, we got 25% uncertainty, so it doesn't really matter. Now, by my reckoning, we should be looking at around 166 hertz for resonance. That's on about 97. That's close to 166. That's obviously a bigger amplitude. There, it seems to be the maximum. I don't even know if you can see it. See if I can get some light on it from a particular angle. Let's try a flashlight on my camera phone. Does that help? You can actually see the shadow better than you can see the string, I think. You can just sort of see the shadow from device is too hot, quality may be reduced. Okay, I've been recording too long apparently, so the camera light's just turned off because it thinks it's too hot. Let's try it again. Okay, so you can see a little bit of light reflecting around here-ish. So that frequency seems to be the one that gives you the largest amplitude, 168.2-ish, oops, 168.2, which I've written there. And there we have it. And this experiment, you can see, takes more than a little while to do. It's the longest one, I think, of all of the required practicals. Now, I've rather stupidly put the uncertainties there, and I'd intended to put extra columns there, so I might have to make some space here. Let's see if we can get that 4th mass per unit length. It'd be quite nice if I could have a graph with 4 points, if not more, but let's go with 4 points and see if I can get that to work. So, again, I'm going to use some tape so I can keep track of the string that's already on there. I'm going to lay it down with the other 2 bits of string that I've put here and here. Get a 4th one, that 4th reel, and so this is just repeating it, so I'm not going to show you this. So these are the results so far. I wanted a higher mass per unit length string, and I found this quite thick sort of parcel string in the prep room. It had already been tied up, so I hadn't measured the mass per unit length of it yet. It already had the knots in it. What I'll do is I'll cut the knots off it and measure the mass per unit length in a bit. But because it was a bit thicker, you could see a bit more clearly the vibration of the string. Now, unfortunately, the way it's working at the moment, the camera refresh is similar. 60 hertz this is being filmed at, and this is currently vibrating at about 56 hertz. So you can kind of see the string shaking up and down. But it doesn't matter. You can see that there is a maximum extent to that shaking. And here, it goes to 0, and then we have the maximum extent again. So what we're looking at here is the second harmonic. Oh, frequency's messing around a bit. So that's the second harmonic with a node in the middle. And we could use the second harmonic instead of the first harmonic if we want. I'm not going to. I'm going to mess around and find the first harmonic, but I just thought it was interesting to show you. That's at around 55.8 hertz, 55.9, 56. It's drifted all over the place. But that's part of the problem, is that the camera's filming at 60 hertz. So let's drop the frequency right down. Maybe about 30 hertz, something like that. See if we can get that node in the middle. Oh, I haven't put the card up. It's better. See if I can get the anti-node in the middle. Oh, big amplitude, even bigger amplitude dropping down. So the biggest amplitude seems to be at that frequency there. 28.38 hertz, which I can write in here. 28.38, and that is 0.01 hertz uncertainty on that. I should have had a column there, shouldn't I? Silly me. I haven't measured the mass per unit length of string 5 yet, but string 5 will be our last string, so let's do that. So let's just cut the knots off at the end, because obviously that's going to affect our measurement of mass per unit length. Let's measure the mass of it first, of this piece of string. Should be a big enough mass that I don't have to mess around with taping it and measuring the mass of the tape to stop it springing open and all that sort of nonsense. Let's get the balance like that so you can see it. Hello, says the balance. 1.49 grams. We know what the uncertainty of that is. Length of the string. Oh, careful I don't knot this up. Length of the string, the usual way. So, 1 meter. 1 point, I don't want to stretch it. 1.56 meters. And the uncertainty of that, I use 2 rulers, so 0.0004 meters. Let's do the calculations. Here it is. So 1.49 divided by 1.56. Wow, that's much bigger. Let's just put all of them. So the uncertainty is 0.01 grams divided by 1.49, less than 1%. And with this one here, it's 0.004. It's 2 millimeters times 2 because there were 2 rulers, divided by 1.56. There we are, not a very big percentage at all. Add them together, so less than 1%, divided by multiplied by 0.5. Let's use the unrounded number. 0.9551 blah blah blah. Oops. 0.0089. There we go. Now looking at this, I might not be able to actually use that data point, because what I don't want is all these to be so close together on the scale where we can see this and this, that there might as well be one data point, because if all these are so close together as one data point, then we might get 1, 2, maybe 3 data points. Whereas if I don't plot that, I might be able to get 4 data points plotted. It depends on the scale and what I can get to fit. So we'll have to make the decision about whether to use that point. I'd like to use it because it would increase the range of our results, but not if it means that I can't actually plot these because the points are too close together, so we can't actually resolve them on our fine grid graph paper. So we've now got all the data we need for all 3 practicals. Now it's time to analyse our results. Now, as I said before, for each of these practicals, we're going to plot one thing on the y-axis, one thing on the x-axis, pull off this gradient, and then check that that matches what it ought to match based on our measurements. Can't really reference what it should equal, other than to say that we've already referenced where this equation came from, and so if for every single one of these practicals the gradient equals, or is in the tolerance of what we expect it to equal, then we can say that our result is as expected. That is to say, our result is in line with what we have found online for our reference. So that's about the best we can do for this. Now, I already, for this table, have my F column there and my reciprocal of L column there. So I can just get plotting for that. Title of the graph, so we can match it to the table. Now, starting by looking at what's going to be on the x-axis, we're going from 1 to 2.5. That's a difference of 1.5. Now, I can have 9 squares across here, where 3 squares represent 0.5, but that's possibly going to get a bit messy, because then I've got 30 small squares fitting into 0.5. Let's just see what 0.5 divided by 30 gives us. Yeah, that gives us a weird number per small square, so I'm not keen on that. Let's have a look what else we could do. We've got 90 small squares across, and let's say we go up to 2.5. So 2.5 divided by 90, that still gives us a weird number. Not something we could really use. But then we could, of course, have a false origin somewhere else. Let's keep thinking. Right, so what I thought then is, look, we got to 2.5, so we go 2.5 divided by 90 small squares. That gives us a weird number. But if instead we go 0.02 per small square, so that is, times it by 90 small squares, a range of 1.8 along the x-axis, 1.8 per metre along the x-axis, then we could start at 1 and finish on 2.8, and that would fit quite nicely. So let's do that. The y-axis is much easier. We're going from a little more than 60 to a little less than 160. So basically we're trying to fit 100 into our vertical space. So if we go with 10 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the data will occupy more than half the page. But it's good enough. So we could just fit 100 into 10 big squares. That is 100 little squares. Each little square is worth, well, 1. So I'm just going to go ahead and draw my axes here and hope I've got it wrong. Do you know, if I've made a mistake, I've made a mistake, and I can correct it later, because I'm using a pencil. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I should go up a little bit further, but I'm not going to need it. Always using a pencil. Arrows on the axes indicate the direction of increasing positivity. Now I need to start filling in my labels. So down here on the x-axis we have got length in meters to the -1. That's the label. There's nothing wrong with that as a label. And on the y-axis it's frequency in hertz. And we're hoping to get a straight line. Now let's fill the numbers in. So there's my x-axis scale. I've just noticed that I've recorded these numbers 1.800, 2.000. You might think that's completely pointless, but it does match what these are. That one's got an extra 0, but this is, I think, about as sensible as I want to make it. Now the y-axis scale, that goes up 60, 80, 100, 120, 140, 160, like that. And remember, my little pro tip, I've written what the number of small squares, what the distance, try one more time, the interval on the y and x-axis is represented by a small square. So now all I need to do to work out how many small squares I go along is I'll look at this and I'll say, well, that's an easy one. Let's go 64.2. Well, actually, I don't even need to type that into a calculator. 64.2. This is 60. 64 puts me here. And I'm not going to do the 0.2. I'm not going to interpolate between the fine grid lines. Let's do the next one. 1.25. I might have to interpolate for that one. 1.25 and then 79. 79. There we go. 1.2, 1.3, so 1.25 is there. So it's dead easy to plot this once you've got a sensible scale. And there we have it. 1, 2, 3, 4, 5 data points plotted for the 1, 2, 3, 4, 5 data points. And they look pretty good for a straight line, really straight. Now I do need to do my error bars, which I will do now. You see in the y-axis, the error bars are going to be 0.01 and 0.1 hertz, but it's only 1 hertz per small square, so there's no point doing error bars in the y-axis. So what about the x-axis, this one here? Well, let's just check what the largest uncertainty is. That will be 0.005 divided by 0.4, so that's about 1.25% of that. So let's go with 2.5, multiply it, 0.031. 0.031 is just a small square on the x direction. So it is possible to draw the error bars. So which data point was that? That was the last one. So I can do, should be 1.5 small squares. So I'll make it 2 small squares just to be liberal with the uncertainties. So there we go. There's my error bar horizontally for that one. Let's just check the next one then. So 0.005 divided by 0.4. I've done that one. 0.005 divided by 0.5. That's only 1% uncertainty multiplied by 2 gives us 0.02, which is 1 small square. So yes, I can put 1 error bar in there, very tiny little error bar there. Let's check the others. Don't imagine this is going to give us very big uncertainties now, but we'll just do one last check. So 0.005, which is the absolute uncertainty in the length, divided by 0.6. Try that again. 0.005 divided by 0.6 gives us less than 1% uncertainty, multiplied by the reciprocal, so 1.667, gives us less than half of a small square. So I can't draw the error bars on these. So I can only draw those 2 error bars. Well, there we go. That's the graph done. Let's analyze it. When drawing the line of best fit, I would recommend you rotate the paper around, but not just connecting the first point to the last point. It goes too far away from that point as it is. So let's adjust this slightly. I think that's probably about as good as we're going to get. We have less certainty in these top 2 points, so I'm putting more importance on the bottom 2 points when it comes to lining it up. So I reckon that's the line of best fit. What about the worst acceptable line of best fit? Well, let's push this down a bit. Could argue there, perhaps, is just going through, but I think that's barely acceptable. So we've got our 2 lines of best fit there. We've got the top one, which I'll label 𝗟𝗶F, line of best fit. I've got the bottom one, which I'll label worst acceptable line of best fit. Let's pick some points on the lines to do our gradient calculations. Anywhere it goes nicely through grid lines. Well, it does about there-ish quite nicely. Let's pick a point all the way down here. There is probably as good as we're going to get. So we can put our coordinates for them in a second. Let's look at the worst, that's on the worst acceptable one. So let's pick one on the line of best fit, or possibly there. And on the worst acceptable line of best fit down here, let's pick that point there. So I can write the coordinates of those on. That's what I like to do. There we go. There's my points labelled. Now I can do my gradients. Make sure I'm writing the numbers with the same number of significant figures so I can easily track where the numbers are coming from and where they're going. Now I'll type in my gradient calculation. So 151, 71 subtract 2.42, 1.1 subtract divide, and I get 60.6. I am going to have to think about units. That's hertz per meter, so hertz meters, or meters per second, which is a speed. That's nice. About 60.6 meters per second. And there we have it, the worst acceptable line of best fit gradient calculation done. Just be careful you're picking the right numbers. Difference between them is going to be the uncertainty. So it's just that subtract that is that. And so 60.6 plus or minus 3.3 meters per second is the gradient. But is that equal to this term here? Well, let's just use this space down here rather than start a new page just to calculate what that should be. Well, I've just done the calculation, so using that number and that number, but be careful, it's grams per meter. So this is multiplied by 10 to the negative 3. Plugging that number and that number into that equation gives us 61.4, let's just say 3 meters per second. The uncertainty in that I need to calculate as well. So let's do 0.059 divided by 2.943. That's the relative uncertainty in that. 0.0054 divided by 0.195. That's the relative uncertainty in that. Add them together, and now because it's under the square root, we have to divide it by half. So that is the relative uncertainty in that. So we multiply that. I've got the number stored in my calculator, so I don't have to do any dodgy rounding. And it's, give or take, 1.5. So let's write that as 61.4 plus or minus 1.5 meters per second. So I've included the uncertainties. And we can see very, very clearly, we don't even have to draw a number line to see that that and that overlap. So from the first practical, we can see that that is in agreement with the equation that we are testing. Our results agree with expectation. Now let's do practical 2, so I won't have to turn the page quite as often. Sort of something to add. Root t over root mu is the speed of the wave. So this is half the speed of the wave. So the speed of the wave is actually double that. But anyway, let's move on to practical 2. Scales! We've got to work out the scale. And we're plotting f on the y-axis, going from just under 40 to nearly 100. And we're plotting root t, that is square root of that, that's the same thing, on the x-axis. So that's from just under 1 to just over 2.6. Right, let's put our thinking caps on and work out what the scales are going to be. So horizontally our range is from about, let's go 2.7, subtract, let's say 0.9. So it's about 1.8. Ooh, that's quite convenient, because there is 1, 2, 3, 4, 5, 6, 7, 8, 9 big squares. And therefore it's 0.02 per little square. Hey, that works out well. 0.02 per little square. Does mean I'll be going right to the edge, which I'm not keen on, but that doesn't matter. Right, now, next one, the y-axis. So we're going from, let's say, 39 to 96. So 96 subtract 39. So 57. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 140 small squares. Don't like that. Don't like that. We're going to say 0.5 per little square, though. We say 0.5 per little square. That will work, because if it's 0.05, I think, it's 0.05 per little square. Let's just check that again. 96 subtract 39, 0.05 per little square. Ugh. Try again. 96, everyone makes mistakes. Subtract 39, 0.05 per little square gives us, it is 0.5, not 0.05. 0.5 per little square gives us 114, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, so that's fine. So 0.5 per little square starting from 39. I don't like it. Actually, it'd be better if I'd shifted this a little bit. because I don't like the odd numbers here. I'd much rather have nice even numbers, but it's okay. It would be much nicer if I'd shifted it. Doesn't matter. I've done it now, and it's done in pen. So that it works. It may not be pretty, but it works. We only go up in tens, but we just seem to have shifted to a weird number. Right, so the x-axis is perhaps a little bit nicer. This is t in newtons, all under the square root. It's perhaps a little bit nicer. I've got the false origin starting at 0.90, and then I've written 1.0, 1.2, 1.4, 1.6, and so on along there. Matching the decimal places here to actually this scale here, because I don't want to have to write lots and lots of zeros. I couldn't get it to fit. Right, point plotting time. And there they are. There's all the points plotted. And yet again, it makes quite a convincing straight line, although it does seem to curve at the end. A little bit. It does seem to have a slight curve on that. Yeah, but that could just be random error. So let's get our error bars in there. Straight away, the error bars in the y-axis aren't going to be doing anything. 0.01 is the uncertainty in the frequency. Let's divide it by the smallest one. 39.07. See what percentage that is. Actually, I don't even need to do that because it's not doing anything with it. Look, y-axis, frequency 0.5, that's less than that. So I cannot plot the error bars. The uncertainty is less than the error bars would allow. How about the x-axis? Let's do the uncertainty in that. Well, it's going to be half of the relative uncertainty in m. And the relative uncertainty in m is about 3%, let's say 2%. There's going to be half of that. So it's about that proportion of each of these. So let's take the biggest one and see if I can get the error bars to fit. It's 2.62, multiply it, and in the x-axis, no. Look, the uncertainty, even for the one where it would have the biggest uncertainty, is coming in smaller than the x-axis. Actually, it's a little bit bigger. I might just be able to get error bars just on that one of 1. Let's say round it to, is 1 square. But the errors are getting smaller as we go down. So let's just test the next one. The uncertainty is, I think I said it was something like that. Let's just work it out. So it was 2%, but it's under the square root, so it's half of that, multiplied by, let's say, 2.426. Don't need to do that in the calculator, but I did it anyway. So 0.24, 0.2. Yeah, we can have 1 small square error bar on this one as well. If we can do error bars, we should do error bars. Now let's have a look and see whether I can get it to work with the next one. It's 0.01 multiplied by 2.2. So that one will have an error bar as well of 1. That one will have an error bar of 1. That one will have an error bar of 1 as well. So all except the first 2 points will have error bars as 1. I'm not going to do the calculation every time. I can see that. Okay. Will that help us? Maybe. We said there was a slight curve, and actually the uncertainty increases as we go up. So yeah, that slight curve could just be random error. That's not necessarily a systematic error, not from what we can see. So line of best fit, somewhere down here, passing through all of the error bars. I think that's about as good as we're going to get. Commit to it, pen goes to line. Right, worst acceptable line of best fit. Let's just try and do another line of best fit. Maybe coming down the other side, something like that. It's sort of one of those, really. I think that one's a worst line of best fit. So let's label this one here the worst acceptable line of best fit, and the one underneath the line of best fit. That's debatable, but that is what I'm going with here. Now I'm going to do the same thing I did before. where I'm going to measure the gradients. The gradient should equal this quantity here. So I'm going to do that next. And because this is just more of the same stuff we've already done, I just went ahead and did it. So that was what we did last time. That's for this one. Line of best fit, I picked my point on this line, and I picked a point on that line, on the same line. Worst acceptable line of best fit, picked those 2 points, wrote the coordinates, the gradient for the line of best fit. You can see that there if you want to check the working yourself. There it is. Worst acceptable line of best fit, calculated the gradient. Difference between them became the uncertainty. So I ended up with 33.8 plus or minus 2.0. Again, I'm using a 2 significant figure uncertainty, which is why I present this to just 1 decimal place, so that decimal places are consistent. Making sure I've got my units there, whatever on earth that means. Then I want to see if that is a reasonable answer. So I go over to here to this equation. That's what the gradient should equal. I plugged in L, it's just 1, and mu, which is this, but careful because it's grams, so it's that times 10 to the negative 3. Plugged that into there, and I got that answer there. Now for uncertainties, I had the uncertainty in L, the percentage uncertainty in L, which wasn't very much, plus half of the percentage uncertainty in mu, which is that divided by that, or relative uncertainty, that divided by that. Now, when I did that and then multiplied that relative uncertainty by what that quantity is, it gave me 0.67, so to 2 significant figures. So there is our expected value, and you can see that our value, plus or minus 2, if I add 2 to that, I get 35.8, 35.81. I can subtract that from there, and so the errors overlap. So the experiment agrees with expected result, which is that equals that within experimental error. Same as here, within experimental error, our results are consistent with what we expect. Now for practical 3. For practical 3, we're looking at this equation, and now we're varying mu. So we're going to rewrite this equation. I'll just write it underneath here. We're going to rewrite this equation in the form y equals mx plus c. So f is going to equal, and that's going to be root t over 2l multiplied by mu to the power of minus 1/2. That is actually the same equation. And what am I plotting and where? I'll use the same sort of red colour I did here. This is going to go on the y-axis, that's going to go on the x-axis, that is going to be our gradient, and plus c is plus 0. So that is what I'm plotting. Now you can see I've got mu. What I don't have is the reciprocal of the square root of mu. I've messed up my table. So I'm going to need to calculate that. F is going to be on my y-axis. So I'm going to make a new table here. Just going to copy the data first of all. I'm going to put F as the first column just because, doesn't matter. And next to it, I'm going to put mu to the minus 1/2. The units of that are going to be meters. I don't like writing it like that. Let's write it as mu in grams per meter to the minus 1/2. I'll write it like that. So that's what my table is going to look like. It's easy enough to do that calculation, so off I go. Oh, let's not do grams per meter. Let's do kilograms per meter. Let's do kilograms per meter. I'll do the conversion at this point. I might as well if I'm doing a bunch of calculations. Doing a calculation, 0.195 times 10 to the negative 3 under the square root, and do the reciprocal, 71.61. That's 4 significant figures, so let's give it an extra significant figure. Not that I'll be able to plot it, but there it is. 0.085 times 10 to the negative 3, square root, reciprocal, 108. That's 3 significant figures, so let's do 4 significant figures. Not that I'll be able to plot it, and I'll do the rest of them. And there we have it. So the question becomes, can I choose a scale so all of these points can be plotted? You don't want the points too close together. because then that's not going to work. So let's start by looking at the x-axis. Now, as I know, I have only got 10, 20, 30, 40, 50, 60, 70, 80, 90 small squares to play with. So what is the range across the x-axis? So it goes from about 30 to about 210. So let's put 210 subtract 30 is 180. Divide that by my 90 small squares, gives me 2 per small square. And with that, we will be able to see the difference between these points. So I can plot all 5 if I have on my x-axis 2 of whatever the hell that unit is per small square. And I can write that up here as I always do. An absolutely bonkers unit that is. Right, so that is my, and that's per square. That is what's going on my x-axis. The y-axis, we've got 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 20, 30, 40, 140 to play with. And we go from about 180 down to, let's say, 25. 180 down to 25. 155. I forgot what I said it was. 140. 10, 20, 30, 40, 50, 60, 70. Yeah, 140. Oh, what a bother. What a bother. Now, I wonder, if we go from 28 and we go up 1 each time, 28 add 140, 168. Oh, it's so close. 168.2, but that's if we're going up 1 each time. And if we go up 1 each time, I wouldn't be able to resolve that anyway. So let's do that. Let's do the y-axis. 1.0, or just 1, I can't do 1.0, hertz per little square. It's going to occupy all of this space, but it's the best we can do. Right at the edge. Oh, right at the edge. I really don't like it, but we've got the paper, so we should use the paper. Make sure you've got a 30 centimetre clear plastic ruler. No way you can draw a straight line without one. 30 centimetre clear plastic ruler to the rescue. Wow. So let's label the axes. I'm going to label this one here. I'm just going to write the label here, I think. Mu in units of kilograms per metre, all to the power of -1/2. And this one here, I'm just going to have to label it here, I think. Frequency in hertz. Let's write our numbers in. And would you look at that? I've messed up the scale. We knew it would happen eventually. I've gone up to 168 because I was fussing about this point down here, which is 168.2. Look at that, that's 180. Messed up the scale. Now I've got 2 choices here. I can either cross out this scale and rewrite one, which is probably what I'm going to do to save space. I don't want to go up to here if I don't have to. Or I could start again with it. But no, clearly this scale does not work because I cannot plot 179 on this scale, and that's the whole reason why I went up to 210 along the x-axis, was to get that data point to fit. So let's think about the scale again. Yeah, I mean, probably the best thing to do, and it's not going to be pretty, but probably the best thing to do is to go with 2.0 hertz per square, because we're just outside the range we need. So halving it means we're still going to occupy more than half the paper, but only just. So this goes from 38 to 48, 58, 68, 88, 98, 108, and so on. So I will just draw over those numbers and correct them. Don't use correction fluid, Tipex and other brands, don't use that. 128. Better would be to cross them out and rewrite the numbers down this side of the scale, but I'm just going to carry on. There we are. Just cross those bits out, because we're only going up to 180, which is going to be around about here somewhere, so I don't need to fill in the rest. It's not a disaster, and mistakes happen, but it shows just how easy it is for these mistakes, these sorts of blunders to happen. Right, now we're going to plot. Easy enough to plot, and you've seen me do it plenty of times, so I don't think you want to see me do it again, but I'm gonna. So 32 is 1 small square across on the x-axis, and 28 is on the x-axis, so it's right there. There's that first point, right down there. Might as well put the last point as well, 207, so that is one small square below the 210, and then on the y-axis, 179, we've got 168, so 178 would be 5 squares, 179 would be one little square above that, so it's going to be right on the one in from the edge. 179, 168, 179.1. Yes, right in from the edge, and where that is 178, 179 rounds to the next one, so it'd be one up from that, so it'd be there. So that is the extent, that is the range of my data points. You can see it's definitely got enough range in the x direction. The question is there enough range in the y direction? Just. Look at that, 10, 20, 30, 40, 50, 60, 70 small squares would be to there, and this is just beyond it, and therefore that is an acceptable scale. Right, let's fill in the points in between. There we have it, that's all my points plotted. That one, then that one, then let's get the 2 pens out so you can follow each one. So 71, so that's that one, then it's 108, which is that one, 193, which is that one, 207, which is that one, and 32.36, which is that one. And the points look like, yet again, they lie on a straight line, which is what we expected. We need our error bars. And I have not written how I've calculated errors on any of these. I just haven't written them. I've talked you through them, so I'm just going to talk through them again. But if I wanted someone to see how I was doing these error calculations, well, then I would have to actually write down what I'm doing. But anyway, frequency. This is, with the exception of these two in the middle there, these are all point. Let's just check those two first. So 0.1 hertz, I'm just checking this one there, where the pen is lined up with, the 179, so 0.1 divided by 179.1 gives me a relative uncertainty of 0.0005, which is way below the 2 hertz that I can actually plot error bars to. So that's nonsense. Let's just check the 28 one, because a smaller number should mean bigger uncertainty. So 0.01 divided by 28.38. What am I doing? I'm doing the same thing again. I'm not doing anything to f. We'll see if I remember to edit this bit out or if I leave it in. The uncertainty in f is already given to us here. And you can see if we could only measure f in the y-axis to the nearest 2 hertz, they're all much smaller than 2 hertz. So the uncertainties in these are going to be less than we can draw error bars for. So let's check our reciprocal of the square root of mu. Now the uncertainties I've got here, so let's start with the first one, 0.0034 divided by 0.195. Now I've got to do it this way round to get a relative uncertainty because we have the square root, which means I am halving that relative uncertainty. Then I'm multiplying it by the value, which in this case, string 1 is the first one on this list, so that is 71.611, 71.611, and that gives me my absolute uncertainty in that value, which is 0.99, and I can only plot to the nearest 2, so that actually rounds below a small square. I cannot draw error bars for that first data point. We'll do it again. So the next one, string 2, 0.0052 divided by 0.085. That gives me my relative uncertainty. I'm halving it because it's under the square root and then multiplying it by 108.5 to get the absolute uncertainty. 3.3. I can draw that. It's going to be one small square. So which one is that for? That's the one that's at 98, which is this one here. So I can draw one small square error bars in the horizontal direction. Just like that. Then I do the next one. So string 3 is 0067 divided by 0.0267. So what I'm doing there is calculating the relative uncertainty. It's quite high for string 3. Halving it because it's under the square root, and then multiplying it by the 193.5 that I've got for string 3, giving me 24. That's 12 small squares. So the one that's at 168, which is this one, I can draw 12 small squares, error bars. Well, I can do it in one direction, certainly. 12 small squares takes me to there, and it takes me off the scale in the other direction. So very big error bars on that one because of how thin the string was. I was surprised, actually, that data point was so close to the line, given how big those uncertainties were. Let's just check the next one, string 4, 0.0064 divided by 0.0233. That gives me the relative uncertainty of 29%. Halve it, multiply it by this is string 4, so 204.2. And that gives me, wow, so that is 15 small squares. If each small square in the x direction is 2 meters per kilogram, all under the square root, then that is 15 small squares. That's the one at the very top here, 15 small squares. Ay caramba. So that puts it to, from there to there to there. 10, 15 small squares, and goes off the end of the scale. Again, very surprised that that gave me anything meaningful, and I've already done the last one there. So no error bar I can draw, no error bar I can draw, huge error bars. That could be a curve for all I know. But anyway, let's do our lines of best fit, try and get as close to the lines as we can, not deliberately forcing it through any points. Try and get that like that. Probably there is about as good. We're going to get closer to those points because we've got less uncertainty on those points. So probably something like, we could pretty much pass through those points and do that. That's probably the best line of best fit. Now for the worst one. Well, let's say that it's actually all the way over here somewhere and these points down here are wrong. Well, I mean, that's just nonsense. But let's do that as our worst acceptable line. Look at the difference down here. That is rubbish. But it does pass through those error bars there. It passes through that one, and that one. So 3 of the points are in agreement. So let's go with that. We've got our line of best fit, and we've got our worst acceptable line of best fit. You know what we're going to do? We're going to calculate gradients, and we've done it before, so I'm not going to show you those steps. I've just got to show you this because it's so exciting before I carry on. This point here, right on the grid line, is 188, 188. It almost never happens. So exciting. It's Future Keith here again, and once again, right at the end of the video, the camera overheated and stopped recording the video and only the audio. So I need to, the day after I've done this practical, try and explain what I did. Well, luckily I've got enough laid out here. So my line of best fit and the worst acceptable line of best fit, I talked about them yesterday. This is now Future Keith talking, so you're not going to see it as yesterday, you're going to see it as 20 seconds ago. So let's get the gradient of our line of best fit. I've got the points there. So I've done this so many times now. Look, I did it, same thing there and there. It's just more of the same. So we're going to measure the gradient, and I got the gradient of the line of best fit as 0.88732, weird units of hertz, meters to the half, kilograms to the minus half, very, very weird. The worst acceptable line of best fit gradient, you can check these calculations yourself, but I calculated it to be 1.1493 hertz, square root of meter per square root of kilogram. And so the difference between these two becomes the uncertainty in the gradient. So the gradient is the best fit gradient plus or minus the difference between these two presented to two significant figures. So 0.26, hopefully that's clear enough. But is that what I expect? I mean, it was for the previous two practicals, it worked out. Does it work out for this one? Well, what I expected over here was that the gradient would be equal to root t over 2l. So root t, that's the square root of this number, divided by 2l. L is 1, so divided by 2 gives me that. But what about the uncertainties? Well, t is raised to the power of a half, so I have to half the percentage uncertainty in t. So that number divided by that number, so the absolute uncertainty in t divided by the mean t, that gives me the relative uncertainty. If I halve that, that becomes the relative uncertainty in the square root of t, and add that to the relative uncertainty in L, which is 0.005 divided by 1. And when I add those relative uncertainties together, then multiply that combined relative uncertainty by that mean value of 0.8578, it gives me the absolute uncertainty in that value, which was 0.858 plus or minus 0.013. Again, two significant figure uncertainty, so I match the decimal places on the value here. Make sure I've included my units, then I just check. Is the number I measured from my results, does that agree with what I expected from the equation that I referenced at the start? Well, yes, it does. Look, if I take this value here and I subtract 0.26 from it, then it overlaps with this value here. It does. Might have to add that onto it, but yeah, it does overlap. Great stuff. So the experiment agrees with the expected results within the experimental error. All three of them did. Now, we could do a whole bunch of other experiments, of course. We just chose f as the dependent variable. So the minimum number of experiments needed in order to demonstrate... That was a school bell. Typical. The minimum number of experiments needed to demonstrate this equation is valid is 3, because we keep that one as the dependent variable. We need to have two of them independent variables, so every relationship can be tested. What we haven't tested, of course, is the relationship between t and L if mu and f is kept constant, or the relationship between a mu if L and f are kept constant. But if the three we have done show that this is consistent, then that is the bare minimum that we would need to do. And it does work out, as you can clearly see from the results. So I would count that as a very successful practical. It took me 2.5 hours to do in total, including recording the videos. 2.5 hours is about how long we give students to do the practical part of it, and then they get another 2 weeks to do the analysis. But I did the practical and the analysis in 2.5 hours, so it is definitely possible, even though it is a monster of a practical. It is big. Hope you found it useful.